order, I have to write in horizontal way. So this means the superscript T means transpose. If you already learned a little bit about the linear algebra or matrix, right? So actually what I mean is this one. Okay, and I should put a T over here as well, but yeah, okay. And then it's the multiplications. It's just like you put constant numbers into each coordinate and multiply by the original numbers, and you'll get it. And how does it look like when you put it into a graph? Says that now we have vectors u here and vectors v here. And when you sum them up, graphically expression is that you draw a parallelogram and then you draw diagonal vectors there. So these diagonal vectors will becomes the sum of these two vectors. And if you want to multiply by one vector, it just like extend it or like shrink it. Or if you want to multiply by a negative number, then you will get the opposite directions. For example, like minus u, look like this one. Okay. Okay, so the next question is how about subtractions? So for example, like I want to see this one. So how does that, how do you like draw it in graph? So we take it as plus negative vectors here, and then everything goes through. So first you find the negative v vectors here, and then again you draw a parallelogram and sum them up. Okay, so this is your new vectors. Okay, is that clear? Okay, then is the definition too here. So this is a subspace. Of course, like you can think this is a subset of the original vector space. Okay, and actually it is. So this is a subset W. We call it W, a subset of original vector space V. That itself a vector space under the same operations, and it has to satisfy the following three conditions. The first is that it has to contain zero vectors there, and it's closed under addition, meaning that when I give you like any two of vectors in that subspace and you add it up, you figure out that it's still in that subspace as well. And it is the same under the scalar multiplications, meaning that if I give you a random space in that W, and no matter you multiply it by which numbers, you will always get another vector that is in that subspace. Okay. So that is the definition of subspace. Yeah, and I think the most, the one you you would easily miss is the first property there. So just pay attention to it. And okay, then it's the linear combinations. So this is the textbook definitions of linear combinations, meaning that I have a bunch of vectors over there, and I have corresponding scalar there, and multiplied one by one, and then add them up. Okay, so it looks like this one. I would like to write it down in the following way. Yeah, so I missed the AN here. Yep. Yeah, so I would like that. That's just my preference. I would like to express the linear combinations in this way, and yep. And then is the definition of linear independence here. So what's the linear independence? If we have a set of vectors, says that from V1 to Vn, and we try to solve these equations. Meaning that you write down a linear combinations like this one, and then set it equals to 0. Okay, and you start to think about, okay, what kind of potential answer that those A could be. Okay, and if the only solution is that the A has to be 0 for all the small a here, then these vectors are linear independent. Okay, right. Okay, and what if you figure out there is some A that could, I should say that there is some, put it this way, A bar, AN, so it's not totally equal, and we can still solve these equations. Then that means these vectors are not linear independent, which you can simply put it linear dependent. And when that happens, that means you can, you can construct some of the vectors over there, like from V1 to Vn. There is this one vector can be constructed by the linear combinations of the rest vectors. Okay, so why is that?